What's going on, everybody? It's the EV Engineer. It's been a minute since I've made a video, and I've decided to come out with this series on ESP-IDF firmware programming. So the ESP-IDF is the manufacturer's IoT development framework, and it's essentially a hardware abstraction layer that uses free RTOS to allow you to more easily use the device. So if you don't know what a hardware abstraction layer is, or a HAL for short, it's essentially a very low-level API to allow you to use the underlying drivers and hardware without having to deal with explicit memory addresses yourself. And the reason they do that is because it takes a long time to write out all these drivers just to do basic hardware level support. Because if you had to do all this yourself, it would take forever to do anything. So to start, I'm going to be diving into the API reference of this microcontroller, the ESP32, which is my favorite microcontroller. And I'll be starting with peripherals, and specifically everyone's favorite peripheral, the UART. So let's get into it. So the first thing we're going to do is create a new project. And one of the easiest ways to do this is if you just copy one of the examples in the framework. So navigate to the framework path on your computer. And if you're on Windows, this is probably just OS C and then Expressive Frameworks and then the version that you downloaded. Then go to examples and then peripherals. And we're going to be using the UART. And I'm just going to copy the most basic example, which is the echo. So I'm just going to come here. I'm going to Control C, come to my desktop, and paste. And it probably pasted it right here. So we're just going to move this up here. And what I like to do is open this up in VS Code, since that is my IDE of choice. So we now have our working project open. Now, the other thing that we're going to need is a terminal to compile and flash our ESP32. So I have the shortcut right here for the ESP-IDF, which automatically gets created when you install the framework. So all you need to do is double click and it opens up the terminal and then adds all the paths and environment variables needed to use their framework. Cool. So we're pretty much ready to go software-wise. Now, the other thing we're going to need is a ESP32, obviously. And I have one right here. And it is essentially just the ESP32. You can ignore this CAN peripheral. If you've seen some of my other videos, I do a lot of CAN stuff. But I'm really just using 2 pins on the side of the microcontroller, which is GPIO 16 and 17. So there's nothing too crazy going on here. And then I have this USB to UART converter. And it's literally just TX and RX and then USB. And I'm just going to plug that into my computer. So I have the ESP32 connected to my computer, and that is COM3. And now I'm just going to connect my USB to UART converter. And we can see that it is COM4. So we're going to be using PuTTY just for basic readout and sending of characters. So PuTTY. And I'll enter the parameters later for the serial, since it depends on what the driver is expecting. But let's just keep this in mind. So let's now get into the C code. So we're going to open up main, and we're going to look at this example. What I'm actually going to do is start from scratch here, because I think it's a little more helpful if I do that rather than just reading the example. So I'm going to make a copy, and this is going to be like our backup. And I'm going to use this one as our working code. And I'm just going to delete all this stuff. So let's get started. The only thing I'm going to leave here is this task. So we're going to be using free RTOS. And without getting into the mechanics of free RTOS too much, there is essentially a function here, which we call a task. And then the xtask create is pretty much going to allocate this task a bunch of stack space. and then it's going to, it's going to manage sort of that task. And that's not really the point of this video, so I'm going to leave it at that. So let's just go down to this functional overview. So it tells us that a typical workflow is broken down into the following sections: set the parameters, set the pins, install the driver, and then run your UART stuff. Now 5 and 6 here are optional, which is essentially using interrupts for UART communication, and I guess deleting a driver if you wanted to do that. So they say right here 5 and 6 are optional, so we're going to be focusing on the first 4. So I'm just going to copy this so that we can have a little reminder of what we're trying to do. And I guess I should tell you what we are trying to do. I'm going to set up a simple UART project such that we can type in the PuTTY terminal and receive the characters on the ESP32, and then have the ESP32 transmit those characters back to PuTTY. So we have a so we sort of close the loop on this system, and we know that everything's working. So let's go to the communication parameters. So they give us some example code here, which is using the UART config data structure, and then it's passing that to the UART parameter config haul function. So this is an example of a haul function I was talking about. It's sort of wrapping the underlying functionality of the UART so that we don't have to deal with it. So I'm going to copy this, and I'm just going to put this all in our new task. Fix the indentation, and you can see here that it's using UART num2. So there are 3 UART controllers on the ESP32, and I'm just going to use UART num2 at random. Cool. So moving on, let's set the baud rate to the standard 115200. We're going to be using 8 data bits, no parity, 1 stop bit, and I don't want to use flow control. So yeah, I kind of found out from our backup that we can just use this macro here for disabling flow control. And I don't know what this is, but I assume it has something to do with disabling the flow control. So let's just copy that. Cool. So we have all the parameters that we need to set up a UART with no flow control and pretty standard parameters. So they give a little explanation here. If you want to do each individual parameter, one at a time, you can use these functions, or you can just use this whole data structure. So yeah, we're now done step 1. So let's go to step 2. Let's set the communication pins. And like I mentioned, I have these 2 cables connected to pins 16 and 17 on my ESP32. So those are these pins right here, GPIO 16 and 17. I sort of just connected them to the TX2 and RX2 because I figured we're using UART num2, and it just kind of made sense to me to use those 2 pins. But yeah, let me know in the comments if anyone uses other pins and this works. Anyways, I use these 2 pins. So we need to set them. So I'm just going to copy this. I'm going to go here, and I used 16 and 17. Actually, I think the order is 17 and then 16. And then I am not using flow control. So they actually tell us here the same macro UART pin no change should be specified for pins that will not be used. Perfect. So I'm just going to copy this, and then I will put it here, and I will put it here. There we go. So step 2 is now done. Moving on. Step 3, let's install the driver. So they give us a bit of explanation here. We need to call the UART driver install and specify the following parameters. We need a TX ring buffer, an RX ring buffer, an event queue handle and the size of that queue, and some flags to allocate an interrupt. And let's just copy this example code. And we will indent. So they are using a UART size of this. So you can see the UART num2, UART buffer size, which is our buffer, some RTOS Q, and 0. I'm pretty sure the 0 actually disables interrupts, because if we look at the example here, they have this config UART ISR, which only gets set if you specify it in the project config. So presumably we're just disabling interrupts. And then this 10 here, what does this mean? So one thing we can do, since we're actually staring at the API reference, is let's go to the reference. We're now looking at the UART driver install. UART event queue size. Okay, the size is 10. Cool, so let's go back. So we now have the driver installed using this function, and apparently we are now ready to use the UART. So let's come down here, and they give us some explanations of how this works. So pretty much, if you want to write something, put it in the TX FIFO buffer, and then the finite state machine, which is just happening in the background, handles the rest. So we only need to care about step 1. And inversely, if we want to receive data, the finite state machine does stuff in the background, and then we just need to read from the RX FIFO buffer. And they give us these two functions, UART write bytes and UART read bytes. So let's start with transmit data. So I am now on the left side of the screen because I was looking at the recording, and I figured I should probably increase the font size. And if I do that, I run out of space. So now I'm over here. Anyways, so moving on, we're going to transmit data and see what happens. So after preparing the data for transmission, we just need to call this UART write data. I'm going to copy this code for now and move it right here. And we have a little message. So this is a test string, and we are now writing this test string. So now let's compile our code. So we need to go to the write path. So I'm going to copy this, going to cd into here, and idf.py build. So we did actually run into one build error, and it's saying that it doesn't know strlen is. So what we need to do is include string .h. So let's now try again. And it doesn't know what echo task stack size is. So echo task stack size is one of those things we deleted, and it's just config example stack size. So if we search for this, it's just 2048. So let's see if we can replace this and it compiles. Cool, so it looks like it finally worked. So we're now ready to flash the code. So we're going to do idf.py, and if you remember from earlier, we're in com3 flash, and I also want to monitor, and it is now flashing. Interesting. Your echo task should not return. Aborting now. Oh, okay. I think I know what's going on. So one thing that FreeRTOS really does not like is if you reach the end of your task. So what I'm going to do is wrap this in a while one and put this in here. That way FreeRTOS doesn't freak out. So let's quit this. Let's build one more time. And let's try to flash and monitor again. Connecting, press the button. And there we go, it's not complaining anymore. So now let's open up PuTTY. And if you remember from our device manager, it is COM4. And let's set the baud rate and let's open it up. And there we go. We're getting a lot of messages and it looks like we do not have a carriage return. Okay. I will put a carriage return and I will compile one more time, but this is unnecessary. We already know it works. So this is really cool. We know that we can transmit from the ESP32. So now what we need to do is figure out how to receive data from the ESP32. So let's now move on to the next section, which is receiving data. And before we do that, I'm just going to quickly show with the new carriage return, that looks a little cleaner. Awesome. So now that we know that transmit works, the last thing to do here is to set up receive, and then we can finally receive data from PuTTY and transmit it back to PuTTY. So we can see on the left here, the section on read data tells us that we need to use the UART read bytes function. And optionally, before reading the data, we can check the number of bytes in the RX FIFO buffer. But I'm not going to do that. In a second, you'll see why. So let's make our data buffer, which I'm just going to call data and give it 128 bytes. And we don't need this anymore. And next, we're going to copy the UART read bytes function from this example. I'm going to paste this here, and then I'm going to get the length of the number of characters that we just read. This length right here is actually the number of bytes we're going to read in. So let's just quickly verify in the reference the UART num. So we're using the UART num from above, pointer to the buffer, which is this array that I've defined on the stack. Data length, I'm just going to read in pretty much the size of the buffer, but I'm going to read in one less byte, and that will become obvious in a minute. And this one ticks to wait. So this means the way we currently have it, that we're going to wait every 100 RTOS ticks to pull in the data. I'm actually going to change this to 10 RTOS ticks because I tried this before and it was a little laggy with the hundreds. And now what we're going to do is we're going to write what we just read back to PuTTY. So UART write bytes, UART num, const char, and instead of test string, we will give it data, and we're going to give it len. Very cool. So this is pretty much it. And we can just compile. UART read bytes, too few arguments. Forgot to give it data. In the example, they have this little section of code here. And what this is just doing is on the actual monitor, it's going to print out the characters it sees, which is like even more feedback that everything's working. So if len is not 0, we're going to add this null character at the end of our string, which is required in C. And so now you can see why I did one less character on our buffer so that we can append null to the end of it. And we're going to log this. So this tag, we're going to need to write a custom tag. So we'll say UART test and then pass in data. So this should compile. Perfect. So now let's flash onto the ESP32. Finally, we can do our test. So let's pull up PuTTY, and we should be able to type, and we see something. So we are now getting the characters that we type into PuTTY back to PuTTY, and we can see from the monitor log what it's actually seeing. So I'm going to type hello space world. This is the EV engineer. And what's interesting is if I type really quickly, so I'll say, hello, this is blah, 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 you get many characters on one line versus if I just type slowly, you only see one at a time being logged. And that has to do with the rate at which we are sampling the incoming data. So right now I have it set to every 10 RTOS ticks to read the buffer. So before it was 100 and it was 10 times slower. So you can probably imagine it felt a little laggy. This wraps up our demo. We have shown that we can read and we can write data to the UART. So if you made it to the end of the video, thank you very much for watching. And I'll be coming out with more videos on the framework. So anyways, thank you very much. Have a nice day.